Okay, so this is section 1.3. We're going to be talking about angular and linear velocity as it pertains to circular motion. So what is circular motion? It's motion that's going around in circles. So for example, if you have a saw blade, one of our book's favorite examples, you'll see this in the homework set. If you have a saw blade that's spinning and you have a point, let's say right there on the saw blade, it's going to be moving, when the blade is spinning, it's going to be moving around and around in circles. Okay? If you have a vinyl record, right, and it's spinning at whatever, 45 RPM, any point on that record is going to be spinning around and around. All right? If you look at a clock and you look at, for example, the seconds hand, it's going to be spinning around and around. All right? Now, that's the kind of motion that we're interested in. In particular, we're interested in this kind of motion, circular motion in a circle, that's constant, at a constant rate. So no speeding up, no slowing down is allowed for our discussion here today. All right. If you do want to talk about speeding up and slowing down, that's going to have to be calculus. Okay, so we're talking constant motion in a circle. So one good analogy to think about when we talk about this section is just regular linear motion, like you're driving along a straight road. We would be, the analogous situation would be driving along a straight road at a constant speed. All right, no hitting your accelerator, no hitting the brakes. You're just driving at a constant speed. Okay, here you're going around a circle at a constant speed. All right, so that's our setup. Our first concept is angular velocity. Okay, so again, let's go to our analogy. When we talk about regular motion along a straight road, driving along a straight road, what is our velocity or what is our speed? It's going to be how far we traveled. So velocity for regular motion along a line is going to be distance traveled over time it took. Right? For example, if we drove 200 miles, right, and it took us 1 hour, then our distance traveled would be 200 over 200 miles over 2 hours. Our velocity would be 100. So we will have been driving 100 miles an hour. All right? Okay. So angular velocity is the same idea, except angular velocity is not going to be distance traveled, it's going to be angle traveled. Let me put that in quotes, over time it took. All right, so what I mean by that is if I have the center of my circle, right, I'm here, and I'm traveling around, again, in circular motion. Let's say I travel to here, okay? And let's say it took me 3 seconds to go from our start point to our end point, all right? So the angle traveled, by the angle traveled, I mean this angle right there, all right? So this right there is that right there, okay? The time it took is the same, 3 seconds. All right. So if I traveled, for example, if I measured this angle to be 45 degrees or pi over 4 radians, then my angular velocity would be 45 degrees over 3 seconds or pi over 4 radians over 3 seconds. All right. If I use 45 degrees over 3 seconds, so if it's 45 degrees over 3 seconds, that would be 15 degrees per second. So those would be my units. Okay. Just like up here with velocity, distance traveled over time it took, right? We talked about miles and hours. This would be miles over hours, right? Miles per hour. Okay. So here, if you use degrees, it would be 15 degrees over 15 degrees over seconds. If you use radians, it would be pi over 4 over 3, right? So let me write radians over 3 seconds. And so this would be pi over 12 radians per second. When we work with angular velocity, make sure you put your units. Again, this degrees per second if you're measuring in degrees, or this radians per second if you're measuring in radians. All right. That's because next we're going to be talking about linear velocity. We're going to be working with kind of physical problems. So you always want to have units, right, when you're working with physical problems. For example, miles per hour. So in practice, what this would mean is that I'm traveling, for example, if I use work in degrees, I'm traveling 15 degrees every second. All right. So one question I can ask is, how long does it take me to travel a full circle, right? So in this situation, right? How long does it take me to travel a full circle? Right? Well, 15 degrees per second. How long do we have to travel to get to, so times seconds, right? This is the quantity that I need to figure out. That should be equal to a full circle, right? And so you can see our seconds should be equal to 360 over 15. And so that's going to be 24. All right. So in this specific motion, it's going to take us 24 seconds to make a full revolution. All right. Okay, so you can kind of already see how useful this is. Perhaps I have something moving in circular motion. I want to know kind of how long it takes to make a full circle. I don't actually have to sit there and time it for it to move a full circle, right? I can just wait for it to travel, let's say, in this example, right? Let's say 15 degrees, see how long it takes, and then I can calculate, just as we did right here, 24 seconds. Okay. All right, now, another reason why we want to be very careful about units is just as in kind of linear motion, miles per hour and stuff like that, sometimes you want to use different units, right? So sometimes you want, for example, in regular linear motion along a road, you want to talk about traveling miles per hour. Sometimes you want to talk about meters per second. Sometimes you want to talk about miles per minute, right? So the question is, how do we convert between different units? Okay, so for example, let's say I have something that's traveling in a circular motion, and it's moving 4 radians per minute. All right, so I wanted to specifically do this example here, just to note, this is perfectly legal, right? A lot of times when we work with radians, you see pi's in the expression, like 30 degrees is pi over 6 radians, 90 degrees is pi over 2 radians. But the pi is just there because we're in a way talking about a whole number fraction, a whole kind of a divisible fraction of the full circle, right? And the full circle is 2 pi radians. But it's certainly legal to have something like 4 radians, all right? So let's say we're traveling 4 radians a minute, okay? So what is this in terms of hours? How many radians would this be per hour, right? Or maybe I want to ask, how many radians is this per second, okay? So I think a good way to convert this is to literally write out these words, 4 radians per minute. So let me actually write it again. Per minute, right? We want to convert the minute to hours. And so this is going to be 4. We're leaving the radians, right? We want to keep it as radians. And now we need to convert the minutes to hours. So how many minutes is 1 hour? Well, 1 hour is equal to 60 minutes, right? And so 1 minute is equal to 1/60th of an hour, all right? So that tells me when I convert this this minute to hours, it should be 1/60th of an hour. Okay, and that's it. Now I can just deal with the numbers. So this continues down to here as 4 times 60 radians per hour. Okay, so ultimately I get 240 radians per hour. All right, by the way, a quick check. Does this answer make sense? Should my answer be bigger or smaller than 4? Well, it should be bigger because if I'm moving 4 radians per minute, I'm going to be moving a lot more radians per hour, right? So make a quick check for these kind of physical problems to see if your answer makes sense. All right, on the other hand, if we wanted to convert this same thing, 4 radians per minute into radians per second, right? Then, well, we need to convert minutes to seconds. We know there's 60 seconds in a minute, right? So 1 minute equals 60 seconds. And so 4 radians per minute converts directly to 4 radians over 1 minute is 60 seconds, so 60 seconds. Okay, and so we get 4 over 60 radians per second, which, let's simplify this, is 1/15th of a radian per second. Okay, and again, a quick check. Our answer is smaller than 4, which we expect, because if you're going 4 radians per minute, then every second, right, you're traveling a lot less than that. All right, because a second is a much shorter amount of time. Okay, so this idea allows you to basically do any sort of conversions, right? If I wanted to convert this 4 radians per minute into degrees per hour, right? Then, for example, I could convert the radians to degrees because I know the formula that we just talked about in 1.2 to change those radian units into degree units, right? And then we can do exactly what we just did to convert the minute unit into the hour units. All right, so this is essentially what you would be doing, what you maybe have done in a physics class, right? But probably, of course, not with radians, but maybe with miles per hour to miles per minute or something like that, or feet per hour. Okay, so far so good. Let's introduce another kind of measure of circular motion, and that's revolutions. So we want to talk about this one because in practice, it's used a lot, right? When you hear RPM, that's revolutions per minute, right? And you hear that term quite a bit in a lot of different situations. So the idea is, well, first of all, what is a revolution? What is a revolution? Like if I say 10 revolutions per minute, what does that mean? All right. Okay, so luckily, it's pretty simple. 1 revolution is just going around a circle in entire one time. Okay, so 1 revolution is going around a circle one time. And if I want to convert that to radians, well, going around an entire circle in radians is 2 pi radians, right? And if I wanted to convert that to degrees, 1 revolution going around a circle an entire time is the same as 360 degrees. Okay, so this allows us to convert very freely between the idea of a revolution an idea of a degree, and an idea of a radian, right? So for example, if I have 10 revolutions per minute, and often revolution is abbreviated ReV, right? What is that in terms of, for example, radians per minute? So that would be 10. Well, one revolution is 2 pi radians. We just said that. So that would be 2 pi radians per minute. Okay? And so this would be 20 pi radians per minute. And again, just a quick check. 20 pi is much bigger than 10, right? And that's what we expect because one revolution consists of many, many radians. And so 10 revolutions per minute should consist of much more than 10 radians per minute. All right. Okay, so in this way, right, we can have questions like, if you buy a hard disk, a spinning hard disk, let's say as a backup external drive, oftentimes they're spinning at 5,400 revolutions per minute, right? So the question maybe is, how fast is this spinning in terms of radians per hour, right? Equals what radians per hour. Okay, so, well, you can just convert the the revolutions to radians. So this is 5400 rev per minute is equal to, well, one revolution is 2 pi radians. So this is 5400, 2 pi radians. And as we said, 1 minute is 1/60th of an hour. So over 1/60th hours. Okay, so now we have radians per hour, and the rest of the problem is just kind of cleaning up the arithmetic here. All right, so we're going to end up with 5400 times 60 times 2 pi radians per hour. Okay. All right, I guess let's write this out. So this is going to be 648, and then 123 pi radians per hour. All right, so it's moving quite a bit in terms of angles. All right, so that was angular velocity. That's how much angle you're moving per time. Now we have a second concept, which is linear velocity. And this one here is much closer to what we usually think of when we think of the word velocity. This is actually how far you've traveled, right? So this is over time, right? So if we're talking about circular motion only, constant circular motion, right? We're traveling from here to here, let's say in 3 seconds. Okay. Your linear velocity is going to be this length. So linear velocity equals distance traveled. So notice this is exactly the same idea as straight line motion, right, that we talked about earlier. It's distance traveled over time. Okay, so this would be the arc length of that arc right there, of this red arc right there, divided by time. Okay, so the concept is relatively simple, but notice that in order to calculate this, you have to understand how to calculate arc lengths, right? And so you need the stuff from 1.2. You need the formulas or the understandings of how to get the formulas from 1.2. All right. Oh, by the way, I think I probably should have said, let me just stick it in right here. Just some notation. So we said that angular velocity, just to make sure we got notation straight, angular velocity was angle traveled over time, right? Radians per minute or whatever, right? So this first one is angle over time. And the notation we often use is omega for angular velocity. This is the Greek letter omega, the last letter of the Greek alphabet. So it looks kind of like a W, but it's not. When you write it, it should be kind of rounded. Okay, so linear velocity, we're just going to use v, because it kind of fits more closely to what we think of as the word velocity, right? So this is going to be arc length over time. So remember, we like to use s for arc length, right? So this is arc length. Okay, so linear velocity is arc length over time. All right, but again, it's the same idea as in regular motion, straight line motion. And in fact, it's kind of the same type of idea as with angular velocity, right? It's how far something has changed over time. Okay. All right, so let's do a couple examples here. So if we're moving 2 revolutions per second around a circle of radius 3, what is our linear velocity? Okay. All right, so this is essentially actually a question of converting from angular velocity, right, 2 revolutions per second, and figuring out the linear velocity that corresponds to that. Okay. All right, so how do we do this? Well, velocity, linear velocity is arc length over time, right? And so let's convert. We're moving 2 revolutions per second, right? 1 revolution, let me do this. 1 revolution is a full circle, right? And so if we do a full circle, how far have we traveled? A full circle, if we've traveled a full circle, we've moved the entire circumference of the circle, right? So distance traveled, in other words, the arc length, is going to be 2 pi r, right? The circumference of the circle. Okay, in our example right here, we're moving around a circle of radius 3, so this is going to be equal to 2 pi times 3. All right, so when we move 1 revolution, we've traveled a distance along the circle of 2 pi times 3, which is 6 pi. All right. Okay, so the 2 revolutions per second in terms of linear velocity becomes v equals s, which is our distance traveled, our arc length, which is 6 pi, over, and then we have 2 of those, right? 2 revolutions per second, and then over seconds, over time. Okay, so we've got 12 pi, I guess I should put the units here. Maybe I should say radius. I should probably put a units here. So radius 3 feet, let's say. All right. So this would be 6 pi. This should be 6 pi feet, right? So this would be 6 pi feet. So this would be feet per second. Okay. All right. So this would actually be the physical distance. 12 pi feet per second, we would be, every second, we would be traveling 12 pi feet, right? So if this was a car, our odometer would increase by 12 pi feet, all right? So now here's something interesting. What happens if we change our question to what if we were moving around a circle of radius 5 feet instead of 3, okay? But the same revolutions per minute, all right? Same angular velocity. All right. Well, if we think about it, then what we would have is our v would be 2 times, and then 1 revolution is 2 pi, right? And then our r this time is 5. So it's times 5 feet, right? So this is analogous to this computation up here, okay? And then over seconds, all right? So this is going to be 1020 feet per second. 20 pi, sorry, feet per second. Okay. All right, why is this these two examples interesting? What's happening here, or you could think of what's happening here, is we have, let's say, a spinning disk, right? Our first example, we were 3 feet away from the kind of center of the spinning disk, and we're moving around in circles like this, right? In our second example with the 5 feet, we were a little bit further out. We were all the way out here, and we were moving around in circles. Okay? So what happens is you can see that our linear velocity is different, 20 pi versus 12 pi is different depending on how far we are away from the origin, away from the center of the circle. All right? And in fact, the farther we are from this kind of center, the faster our linear velocity is. And the reason for that is because, well, this disk, the spinning disk, is spinning at a constant speed, constant angular speed, right? And it makes a full circle, in a certain amount of time. But in that same time, both the person out here at 5 feet and the person in here at 3 feet have to move around in a full circle. But the person at 5 feet out has to move a longer distance to make a full circle compared to the person at 3 feet, right? So that person out here has to be moving faster, right? Because they have to make a full circle in the same amount of time, right? And so if you're going to move farther in the same amount of time than someone else, then you better have been moving faster, okay? So this guy out here is moving faster. All right, so that's an interesting thing. And again, something to emphasize here is linear velocity depends on the radius. All right, and in contrast, angular velocity does not. All right. So if you take a look at our angular velocity examples or computations or formulas, you'll see there's no r involved, right? Angular velocity does not care about the radius because it's only about how much angle you travel, right? What radius you are away from the center of the circle makes no difference in terms of angular velocity. But linear velocity, it matters. And again, the way it matters is that the farther you are from the center, right, the faster you're going to have to be spinning. Okay, so we do have two different concepts of velocity for circular motion. How do we move between them, right? If I know your angular velocity and I know how far you are from the center of the circle, then what is your linear velocity? Or if I know my linear velocity, what is my angular velocity? How do we convert between the two? So v, how do we convert that to omega? Or vice versa, right? How do we convert omega to v? So how do we do this conversion? Well, let's say we're talking about this guy here, linear velocity, and angular velocity in terms of the same units of time, all right? So, both are using per second, per hour, per minute, same unit of time, okay? Then in 1 second, let's say, or in 1 unit of that time, how much of the entire circle have we traveled? For linear velocity, in 1 unit of time, if you compare it to the entire circle, we've traveled v over 2 pi r, fraction of the entire circle, right? This is the fraction of the entire circle we've traveled in 1 unit of time. Right, and again, this makes sense. This 2 pi r down here is the circumference of the entire circle, right? And v would be how far we've traveled, what is the arc length of our travel in 1 unit of time. So when I divide these, I get the fraction of the circle that I've traveled, okay? All right, on the other hand, if I look at our angular velocity for the same exact kind of motion, then how much of the circle have we traveled in terms of angles? Well, we've traveled omega angle in terms of angles in 1 unit of time. But how many angles are there in total for the entire circles? 2 pi, right? So we've traveled omega over 2 pi amount of the circle, right? So we're looking at, in terms of pictures, for the left-hand side, if this is our motion here, I'm dividing this guy right here, how much we've traveled, divided by the entire circle, okay? And I'm saying the right-hand side is this angle right there versus the entire circle, okay? So these two guys, these two ratios should be the same, all right? And this gives me the relationship that allows me to convert between linear and angular velocity, right? So v over 2 pi r is equal to omega over 2 pi. There's 2 pi's on both sides. I can multiply the r on both sides to kind of clean it up. So this is the same as v is equal to r omega. Okay, so this would be the general formula that converts you from one measure of velocity to the other measure of velocity. All right, so using this, here's a good question. The equator, let me say it like this. The radius of the Earth is 3,950 miles. All right, roughly. Okay, so the question is, what is the linear velocity at the equator? Let me make it more specific. Linear velocity of a person standing at the equator. Right? Because if you're on the Earth, standing at the equator, right, the Earth is spinning around about its axis, about the North and South Pole axis, right? So that means you're moving around in circular motion. Okay? So if I view from the North Pole, right, the person would be here, you're spinning around. Okay? So the question is, what is your linear velocity? And of course I can also ask, what is your what is the angular velocity of that person? Okay, so that's something for you to think about. And here is a further follow-up question. Do you expect linear velocity, the linear velocity, oops, and again, we're talking about linear velocity due to the rotation of the Earth. All right. To be larger, or let me write like this, to be larger at New York City, or Orlando, Florida. All right. This kind of question actually has some significance in terms of space travel, and maybe you can try to think about it a little bit. All right, so that's it for 1.3, and we're doing only 2 sections this week.